Hello everyone, this is Hamid Azad and my presentation is about diffusion models. Uh, this presentation is mostly based on the paper entitled Understanding Diffusion Models, a Unified Perspective, and it was previously presented in the Journal Club of the CAR group at the University of Ottawa. As an introduction, you may probably hear about DALL-E. DALL-E is an AI system that can create realistic images from the description that is given by the user in natural language. There are three versions of DALL-E released by OpenAI, and the second version, which was released in November 2022, was based on using diffusion models. And this one shows the importance of diffusion models in recent applications of AI. Diffusion models can be considered as a type of generative models. Given an observed data called X with a desired distribution, in general, the main goal of generative models is to learn how to model the distribution of this data, which is denoted here by P of X. Once we learn this distribution, we can use this approximate distribution to generate new samples of the data that we have. There are several types of generative models. Three main categories of them can be seen here. The first one, or maybe the most famous one, is generative adversarial network. In this type of generative models, we have two generator and discriminator networks. As you can see here, the generator network tries to generate new outputs from a random noise input, and the discriminator should distinguish between this fake output and the real image that we have. This procedure would continue until the discriminator wouldn't be able to distinguish between real and fake data. From that moment, the generator can be considered as a generative model to create new data similar to the real data. The other type of generative model is likelihood-based methods, in which the most famous one is the variational autoencoders, in which we have encoders and decoders, as you can see, and the latent variable. And finally, we have also energy-based modeling and score-based generative models. The diffusion models can be shown that has both likelihood-based and score-based interpretations. In order to be familiar with the diffusion models, it would be better to briefly explain some concepts such as latent variables, elbow, and variational autoencoders. For latent variables, think of a data that we can observe, but it is generated by some unseen hidden variables. These variables are called latent, which are mostly random variables and denoted here by Z. To explain the concept of latent variable, the authors use the Plato's allegory of the cave. As you can see in the picture, it's assumed that we have some people chained for their whole life in a cave or behind a wall. What they can see and observe for their whole life is just a two-dimensional projection of what we have in the real three-dimensional world outside the cave. Although these people cannot see the real world outside the cave for their whole life, but they can inference some ideas about the real world based on their observation, their two-dimensional observation. For these people, the 3D real objects are the latent object. Another concept which should be explained here is evidence lower bound or elbow. In likelihood-based generators, one tries to learn a model that maximizes the likelihood distribution of the observed data. This distribution can be calculated using one of these two equations above. As you can see in the first equation, we need to integrate over all the latent variables that we have. And for the second one, we need the latent encoder condition on X or P of Z condition on X. None of these equations is easy to be calculated. Another approach to calculate the likelihood and approximate the likelihood is to use the concept of elbow. The log likelihood of the observed data is called evidence. It can be proved, and you can find the proof in the paper, that the lower bound of the evidence can be calculated using the expectation of the equation that you can see here in this slide. In this equation, Q is a flexible approximate variational distribution with parameters phi, which we try to optimize. Actually, this Q function is an approximate of the true posterior of P of Z condition on X. As it was mentioned in the previous slide, one approach to estimate the likelihood distribution is to use the concept of elbow. But there are two questions that should be answered here. The first one is that why elbow is the lower limit for the evidence or logarithm of likelihood distribution, and the other one is that why we need to maximize elbow in order to estimate the likelihood distribution. To answer these questions, we can use this equation that integration of any distribution over all the values of the random variable that we have would be equal to 1. By using this equation in the first line and by some mathematical manipulations, we can come to this point that evidence or logarithm of P of X would be equal to sum of elbow and KL divergence. As you know, KL divergence is a non-negative value. So since evidence is equal to sum of elbow and a non-negative value, we can say that evidence would be always greater than elbow. This is the answer to the first question. And for the second question, first of all, we should say that what we want is to optimize the parameters of the variational posterior or Q in order to exactly match with true posterior distribution, which is denoted here by P of Z condition on X. So in order to matching these two distribution, and based on the definition of KL divergence, we know that we should minimize the KL divergence to come to this goal. Or ideally, KL divergence should be 0 in order for exact matching. As you can see, the left side of this equation or logarithm of P of X is constant with respect to the parameters that we want to optimize or with respect to phi. Since we have a constant value at the left side of this equality, we can say that minimizing KL divergence would be equivalent to maximizing the elbow, so that the variational posterior would be matched to true posterior distribution. So this is the answer to the second question. In conclusion, we need to maximize the elbow in order to estimate the evidence and then the likelihood distribution, or P of X. After getting familiar with the concepts of latent variables and elbow, it should be mentioned that in the default structure of variational autoencoders, we want to, or we try to maximize elbow. This is equivalent to learning a variational distribution or encoder, denoted here by Q, that transform input into a distribution over possible latents, and at the same time learning a deterministic function or decoder, which is denoted here by P, to convert a given latent vector into an observation. It can be shown that the elbow function can be rewritten by subtraction of two terms. The first term is reconstruction term, and the second one prior matching term. The first term measures the reconstruction likelihood of the decoder from our variational distribution. This term ensures that the learned distribution is modeling effective latents that the original data can be regenerated from. And the second term measures how our variational distribution, or Q, is similar to the prior knowledge of the distribution of latent variables, or P of Z. Maximizing the elbow would be equivalent to maximizing the first term and at the same time minimizing the second term. And we need to optimize elbow with respect to two sets of parameters, phi and theta. The encoder of the variational autoencoder is usually chosen to model a multivariate Gaussian with diagonal covariance, and the prior is often selected to be a standard multivariate Gaussian. As you can see here, both Q and P are assumed to be normal distributions, and by using this assumption, the KL divergence can be computed analytically, and we can reformulate the elbow function. To solve and optimize this function with respect to the parameters, we can use a trick called reparameterization, in which, as you can see, for example, you can rewritten a normalized a normal distributed variable such as x with an average of mu and variance of sigma 2 as a function, as a deterministic function of a noise. As you can see, x equals to mu plus sigma epsilon. By using the same reparameterization for the latent variables, we can show that it can be shown that the gradient for calculating the for optimizing the function can be computed with respect to phi to optimize these parameters, mu and sigma, and thus we can finally optimize elbow and solve the variational autoencoder problem. In the default structure of variational autoencoder, we have only one layer of latent variables, but this structure can be generalized to the case where we have multiple layer of latent variables, in which in this structure, in each layer, the latent variables are at each layer are generated from the higher level latents, as you can see in this slide. This structure of variational autoencoder is called hierarchical. And a special case of this hierarchical variational autoencoders are Markovian ones, in which the generative process is a Markov chain. In other words, decoding each latent variable at layer T only conditions on previous latent or Z of T plus 1. Now that we got familiar with the default structure of variational autoencoders and its generalized forms such as HVAE and Markovian HVAE, we are ready to explain variational diffusion models, which is the topic of this presentation. A variational diffusion model, or VDM, is a Markovian HVAE with three constraints. The first one is that the latent dimension is exactly equal to the data dimension. Based on this constraint, as you can see in the picture in the slide, all the latent variables are denoted by X instead of Z to show that they all have the same dimension. The second constraint is that the structure of the latent encoder at each time step is not learned, and it's instead predefined as a linear Gaussian model. In other words, we can say that it's a Gaussian distribution centered around the output of the previous time step. And finally, the parameters of these Gaussian distributions vary over time, and this variation and these changes is in a such way that the distribution of the latent variable at the final time step, or capital T, would be a standard Gaussian distribution, and with mean of 0 and variance of 1. The picture below shows the structure of variational diffusion models. As you can see, X0 shows the observation layer or data layer, and the last latent layer would be X of T, capital T, which is completely a Gaussian noise. The effect of the three constraints that we had for variational diffusion models in the previous slide is explained here. Based on the first constraint, as I mentioned in the previous slide, we can show both the true data samples and also the latent variables with X to show that all of them have the same dimension. Here we show latent variables by X instead of Z. Based on the second constraint, the distribution of each latent variable in the decoder is Gaussian, centered around its previous latent variable. As you can see, Q shows the distribution and is normal distributed around X of T minus 1. And finally, based on the third constraint, the joint distribution of the data sample and also the latent variables can be shown using this equation, with this assumption that the distribution of the final latent variable, or X of capital T, is a standard normal distribution. Based on what was mentioned in the previous slide, we can explain the relation between the data sample and the latent variables as an steady nosification of an image input over time until it becomes completely identical to uh, standard Gaussian noise. In this case, the encoder distribution denoted here by Q is no longer parameterized by phi and is completely modeled as Gaussian with defined mean and variance parameters at each time step. So in a variational diffusion model, we are only interested in learning uh, distribution P uh, by which we can simulate new data. After optimizing the variational diffusion model, we can simply sample a standard Gaussian noise, which is denoted here by P of x of capital T. And after that, by iteratively running the denoising transition for T steps, we can generate a new data sample, which is denoted here by x0. As it was mentioned in the previous slides, variational diffusion models can be considered as a special case of Markovian HVAEs with three constraints. Based on these three constraints, it was shown in the paper that the elbow can be rewritten using three terms: reconstruction term, period matching term, and consistency term. The first term, or reconstruction term, tries to predict the log probability of the original data sample given the first step latent. We had the same term in the vanilla VAE, variational autoencoder, and so it can be trained with the same procedure that we had there. The second term is the period matching term, and it tries to minimize, and it's minimized when the final latent distribution matches the standard Gaussian. As you can see in this equation, we don't have any trainable parameter in the second term, so this term does not need any optimization. And finally, the last term is consistency term. This term tries to make the distribution of latent variable consistent at each layer from both forward and backward process. In other words, a denoising step from a noisier image should match the corresponding noising step from a clear image at each layer. Uh, this equivalency is shown here by KL divergence, as you can see, and so we need to minimize this term in order to maximize elbow. Based on the new equation for elbow, we can say that optimizing the diffusion models is dominated by the third term, or consistency term. Since all the terms in the elbow are computed as expectations, we can approximate them using Monte Carlo estimates. But the problem is that the consistency term is computed as an expectation over two random variables, x of t minus 1 and t plus 1. In this case, the variance of its Monte Carlo estimate can potentially be higher than the case of having only one random variable. So in the paper, is tried to derive another equation in which we have only one random variable for the last term. As you can see at the top of this slide, uh, we have again reconstruction term, period matching term, similar to the previous slide, but instead of the consistency term, as you can see by the assumptions of having a normal distribution, we can show that the consistency term can be rewritten as this denoising matching term. Uh, by using this assumption of Gaussian distribution and applying to KL divergence, it can be shown that uh, learning solving the diffusion optimization function in the diffusion models is equivalent to learning a neural network to predict the original ground truth image from an arbitrary noisified version of it, as you can see in the bottom of this page. In this step, the authors in the paper try to explain two other presentation of the variational diffusion models. In the first presentation, they used the reparameterization trick again and reformulate the elbow function and the last denoising term. As you can see, by some mathematical manipulation that is explained in the paper, we can show that optimization of the elbow function is equivalent to uh, learning a neural network that try to predict the source noise or epsilon zero, which determines x of t from x0. And so by this equation, it was shown that learning a variational diffusion model is equivalent to learning to predict the noise at each layer. The authors try to explain variational diffusion models using another equivalent in the paper based on energy functions by explaining the probability distribution using energy function as it is described in the paper. It can be shown that uh, the last term in the elbow can be rewritten using this score function s of theta, and to explain the score function, we can say that for every x, taking the gradient of its log likelihood with respect to x is actually describes actually the direction on which we should move in the data space in order to further increase the likelihood of that variable. And the score function actually defines a vector field over the entire space of the data. The previous slides explain the origin of diffusion models and how we can derive and uh, explain the diffusion models. In this slide, we have an example of using diffusion models in the field of object detection. The authors in this paper, Diffusion Model for Object Detection, which is a CVPR paper in 2023, try to use the same, try to use the concept of a diffusion process for object detection. In other words, instead of having noise to image process, which is previously used for uh, generating new samples from random noise, uh, they initialize some bounding box in the image by some random position, and then by learning this diffusion model, they try to detect the objects in the image. So as they say, instead of using a noise to image process, they have noise to box process. As a conclusion, diffusion models can be categorized as a special case of Markovian HVAEs, in which by using the concept of latent variables, it's possible to generate new models from random Gaussian noise. Thank you for your attention.